Hey guys.
Professor,
What's up?
I don't know if you ever saw it, but there was from one of the, I think one of the medical museums, there was they were to get pretty much like, a blood clot.
Yeah. Uh-huh.
There was one that like somehow, I guess it was like a huge blood clot to where it was like almost all the body.
Oh, wow.
And they would pull all of it out
Dang.
in one piece. So it was like they have it on display as kind of showing the circuit on it.
Wow. That's pretty crazy. Can everyone on Zoom hear me okay? I'm using the lectern computer right now, so I'm not using my laptop. So
Yeah, you sound good.
you're good? Okay, cool.
How was your Labor Day weekend?
It was good. Yeah, I went up to I visited Joshua Tree. So I had never been there before, but my fiance's been, and so she took me there. So we did some hiking, we looked at rocks, we looked at trees. At night it was beautiful because we went on a night where the moon wasn't out, and so we could see the stars really well. And so it was really nice. It was tiring and it was hot, but it was a lot of fun.
That sounds really cool.
How was the wind?
The wind?
Yeah.
Not that bad. Actually, I wish there was more wind because it would have been nice to have a breeze, but it was pretty still. And so the only thing you could feel was just the sun's anger at you all day.
Even at night, no wind.
Yeah, no, not that much wind at night.
Wow.
Yeah.
Because the past couple of times I've been to Joshua Tree, I could be confusing with Calico Ghost Town, but there would always be some type of wind.
Yeah, not that much. A little bit of a breeze, I think, but yeah, not too much. Nick, could you put your mask on?
Afternoon, Dr. Chung.
Hey. How's it going?
Not too shabby. Sorry I couldn't be there today in person.
No problem. How was your long weekend?
Busy. Busy doing homework and working on senior design stuff. The two files that you had us download for the bike activity, number 2, right?
Yep.
One of those files was, or there was a couple files, a crank assembly and a cycle chop.
Yeah,
Whatever.
yeah.
Those
yeah.
are SolidWorks files.
Yeah. So we're gonna use that on Thursday. So the crank one is the one we're gonna use mostly in class, and then the other CAD file is for an additional activity for your for the homework. Yeah, but we'll do that on Thursday. Today we're doing one more lecture just because I like to keep the activities on kind of the last thing of the week.
Works for me. Just wanted to make sure that if I needed to have Workbench open, I had ANSYS open.
Yeah, not today. Yeah, we're gonna do it on Thursday.
All good.
All right, it's 5:30, so let's go and get started today. All right, good evening, everyone. How's everyone doing today? Good. So I'm trying something new. So I'm using the lectern computer here instead of my own laptop. Partially just so because I don't have to lug my laptop around, but also it gives me more space to write here. So I think I tested on Zoom. It seems like the audio for that's okay. But in the classroom, I have this, one thing I don't like is I have this giant computer monitor in my face, and so if it's a little bit hard to hear me, just let me know, and then I'll kind of step aside and then kind of stop from there. Okay, but I want to try this just to see how it goes, and if it goes well, then I'll use this. But if not, then I'll go back to my laptop. Okay. So the plan for today is we're going to do this is kind of the very last day of review that we're going to do for today, for this semester, and today we're going to be reviewing a beam theory. Okay, and so it's another lecture day. And on Thursday, that's when that's where we're planning to have our next ANSYS activity. Okay, and so before the class on Thursday, and I'll give some warning about this too. If you can have Workbench open before the lecture on Thursday, I think that'll help speed us up and getting us into the activity. Okay, but for today, we're just doing a regular lecture. Okay. Another announcement I want to make is that the last activity was due on Friday of last week. So I think I graded those over the weekend. Okay. And one thing I forgot to mention in this class that I should have mentioned before is that for, you know, and I have this policy with all of my electives that I usually grade your homework assignments, you know, they're based on completion. And so, you know, my whole stance with electives is that, you know, you guys didn't have to pick this class, but you chose it because you want to be here, you know, because you want to learn the subject. And so, you know, I want to give you guys some additional flexibility with the homework because I know with your required classes, I know a lot of you guys are seniors too, that senior design and stuff can get really busy. And so, you know, as long as I can see that you're putting in an effort for the homework and that you produced a plot, it doesn't have to be the correct plot for the ANSYS, then I'm going to give you credit for that. Okay. And so that's just to kind of give you guys, you know, just so that you're not stressing on getting the exact numbers or the exact plot that I'm looking for. You know, just do your best, and then as long as you can, you know, show something, then I'll give you credit for that. Okay. And so, you know, I think for this first assignment, you know, it didn't really matter too much because I think everyone pretty much got it because it was a simple case. But once we get to some of the more advanced ANSYS stuff, then, you know, just, you know, do your best. And then if you run into issues, you can feel free to talk to me after it's due and we can try to work those out. Okay. But, you know, yeah.
Will there be any solution released for the activities?
Yes. So usually I put out the solutions after I grade them, but I forgot to do it for this one. So I need to put up the solutions for this first activity. Yeah. Yeah. I always do that but I usually wait till after I grade before I do that. Okay. So are there any questions on anything before we get started today? Okay. All right. So let's go ahead and jump right in. Okay. And so the topic for today's lecture is going to be a review of beam theory. I say review, but you know, I don't think that I ever really formally learned beam theory myself when I was in college, but my statics and strength and materials professors were a little bit sus. So, you know, maybe I was supposed to learn it and we just never got to it. I also never learned about drag and lift when I was in my fluids class either. So, you know, but I know for sure that my fluids teacher was kind of on the way out. So my old fluids teacher back in college would take, you know, the first 5 minutes of lecture just to like kind of walk down the stairs to get to the front of the class. You know, which was annoying at first, but then when later when I found out that he was actually in an airplane accident and he survived the airplane accident and his leg has been permanently crippled since then, you know, I gave him cut him a little bit of slack for that. Okay, so beam theory, right? And so beam theory, you know, it's beam theory just in general is really useful to learn. Not really for all the equations because there's a lot of equations that come into it. But I like to think of it as, you know, a way to build kind of intuition and to kind of build a conceptual kind of feel for how beam-like structures will respond to stress. Okay, and so beam theory is the study for how structural beams deform and respond to external loading. Okay. Right, so very much within the themes of this class where, you know, in general in this class, we're interested in seeing how structures in general deform and respond to loading, but, you know, beam theory is kind of very specific things to beams, okay? And so let me draw you out, you know, what kind of my version of a beam looks like, okay? And so very simply, you know, a beam can just be any kind of a long, slender structure, okay? Here I have a cantilever beam, and so on one end it's completely fixed, okay? And the other end it's free, okay? Let me go ahead and draw the coordinate axis here. And so we have our x-axis. So the x-axis points down the beam, down the length of the beam. And the y-axis points downward, okay? Some terminology that we have here is that the x direction we call this the axial direction. Okay. And so that's the, that just refers to going down the length of the beam. And the y direction, this is the transverse direction. Okay. So transverse meaning that it's perpendicular to the long axis of the beam. Okay. All right. And so on this beam, we can expose it to some external loads. Okay. And so we might have, maybe let's say that we have a point load P. Okay. And so we'll study a case like that. Okay. Or another way we can load the beam is we can have a distributed loading. And so we can have a load that kind of distributes kind of evenly across the beam, maybe something like this. Okay. Okay. And so that might be some kind of pressure load or maybe some kind of line load that we put on top. Okay. And then in response to this loading, the beam's going to deform. Okay. And so let's say that the beam kind of deformed exaggeratedly, kind of like that. Okay. So it kind of dips down. And what beam theory will allow us to do, right? And so it's basically, legit beam theory is a collection of basically differential equations that governs the displacement and the stresses in the beam. Okay, and we can solve those equations for the transverse displacement. Transverse displacement or the bending stresses in the beam. Okay. All right, so those are the things, those are the quantities that we're going to be mostly interested in when we're working with beam theory. Okay. Okay. Any questions on this so far? Okay. All right. And so if we cut open the beam, let me draw kind of two kind of cross sections here. Okay. And so if we cut open the beam, a beam that's under loading, we'll primarily see kind of two main loads that the beam is going to be supporting. Okay. No matter how you're loading it on the outside, each cross section of the beam, usually you're going to have some kind of transverse shear. Okay. And the way that we denote transverse shear is that we, give it this direction here. Okay. Okay. So remember, shear stresses are parallels to the face on which they act. Okay. And then the other quantity that we can, that's present in a beam usually is some kind of bending moment. Okay. And so a bending moment is given by, a moment M, which we'll denote just like that. Okay. Right. And so these forces or these reactions that I'm describing here, these are internal forces or internal stresses that occur within the beam. Okay. So remember we talked about last Thursday that structures always, in order to maintain static equilibrium at every point within its structure, it has to develop these kind of internal forces or internal moments in order to balance those stresses. Okay. Okay. All right, so let's go ahead and write out the equations for the beam, okay? And so, we're not going to be solving these equations here, but these are just to kind of show you what equations govern these beams, okay? And these are basically a simplification of the general, elasticity equations that we normally use for structures, but they've been specialized specifically for beams, okay? Because believe it or not, you might not believe it when you see these, but these are actually a lot simpler than kind of the more general equations. All right, so there's a lot of variables here. So first, let me define what they are. Okay. All right, and a lot of these are going to be functions of x, and so they vary along the axial direction of the beam. Okay. So first, let's define the transverse displacement. Okay. And so the transverse displacement is nothing more than just the transverse, deflection of the beam. So how much the beam is going to deform in the y direction. Okay. And we give that the symbol y of x. Okay. Next, we have the transverse shear. Actually, we've defined it up there. Okay. Okay. So the transverse shear is just the internal shear stresses that develop within the beam. Okay. This is also going to be a function of x, and so it can change along the length of the beam depending on what the loading situation looks like. Okay. Next, we have the bending moment. Okay. Which is also a function of x, and so we have m of x. Okay. And then the last variable that we'll have that can vary with x is some kind of distributed loading. Okay. Okay. And so we'll give this the symbol q of x. Okay. And so a distributed loading is just some kind of external load that's distributed along the top. Okay. And so this doesn't account for point loads, and so usually we account for those in a boundary condition. But if you have some kind of distributed loading that is present throughout the entire beam, then we have to work those into the equations just like this. Okay. And a couple other quantities of interest that we'll see. I want to fit it on this page, but it's a little bit tight here. So a couple other parameters that we have to keep in mind for beams is the Young's modulus. Okay, so you'll see these show up in the equations. And so this will have the symbol E, just like we normally give it. Okay. So we talked about the Young's modulus before, and so I won't go into that again. And then the last parameter that we'll look at is the moment of inertia, which is given the symbol pi. Okay, and so the moment of inertia is a property that depends on the shape of the cross section. Okay, and so depending on what type of cross-sectional shape your beam has, whether it be an I-beam or a cylindrical beam or it might be a square beam. Okay, all those have different moments of inertia, and that's going to affect the displacement of the beam or actually all the quantities, just purely from a geometric factor, okay? Because different shapes will distribute the mass of the beam in different ways, and then that's going to have an impact on the results. And all of those different shape effects are basically summed up in the moment of inertia. Okay. All right. Any questions on this before we jump into the equations? Okay. All right, so let's list out the equations. And so there's quite a lot here. Okay. And so first, and they're kind of grouped into different categories too. Right? So let's first go over the bending moment shear load equations. Okay. And so the bending moment shear load equations look like this. And so we take the derivative of the bending moment as a function of x, okay? This is going to be equal to the shear stress, the transverse shear stress as a function of x, okay? Then we have the second derivative of the bending moment as a function of x. This can be equal to minus q of x, okay? It's going to be minus the distributed load. Okay. And so for a case where you have a distributed loading, this is a way that you can solve for the bending moment and also for the shear, the transverse shear, okay? And so usually the way these equations are used is that you are given q of x. Okay. And so you're given the external load, and so that's that's not too different from our finite element cases. And then you use the equations to solve for the internal reactions, okay? The internal bending moments and the internal transverse shear. Okay. Okay. And then once you have the transverse shear, you can relate that to the transverse displacement of the beam. Okay. Okay. And so basically, what you're going to do is you're going to take these equations here. Okay. Or once you solve for v of x, you're going to plug it in down here, and you can use this to solve for y. Okay. And so the equations for that is v of x is equal to minus ei triple derivative of y dx cubed, okay? Right, and so this will give you y once you solve these differential equations. Okay. Okay, so that kind of forms kind of one kind of closed system right there, okay? Right, but what if you wanted to relate the bending moment and the displacement, okay? Right, and so these equations are called the bending moment displacement equations. Or there's only one equation, sorry. Okay. And so to relate the bending moment and the displacement, we have a second derivative here, okay? And so we have m is equal to minus ei times second derivative of y with respect to x. Okay. And so if you wanted a relationship between m and y, there's that's your equation, okay? Right, and then finally, if you wanted to relate the distributed loading with the transverse displacement, you can do so with these equations. Okay. Okay, we can have q of x is equal to ei times the fourth derivative of the displacement. Okay. Okay. And so for the case where you're given the distributed loading q of x and you're only interested in the displacement, you can solve this differential equation here. Although it's a fourth order one, and so you're going to need a lot of boundary conditions for that. Okay. Okay. And so are these the equations you guys learned when you learned beam theory in your previous classes, or do you guys use different ones?
They kind of look familiar.
Familiar? Okay. Okay. Yeah, I don't even know what's traditionally thought, what's traditionally taught, because these are the equations that I found, looking up, beam theory, in kind of some references that I have, but I have no idea if these are the ones that are actually taught. So but I do know that it's these equations here are actually the starting points for kind of some more specialized finite element theory. And so we're not going to be covering that in this class because I did that last semester and it wasn't that popular, but these you can use these equations as kind of a starting point for FEA too, because remember what we said FEA was. So FEA was just a way to solve differential equations like these in a computational manner, right? And so when you have differential equations, you can always use finite elements on that. And so some very specialized methods have been developed around these equations here. But we're not going to get too much into the details about that. Okay, so any questions on this so far?
Is that a dm over x equals u of x or minus u of x?
It's a v of x. It's just it's a positive v of x.
And that's an equal sign?
Yes. Mhm. Okay. All right. And so, those are all the equations there. Okay. Let's talk about a way to compute the bending moment. Okay, or the bending stress. Sorry. Okay. Okay. And so the bending stress, you can compute this from the bending moment. Okay. Okay. And basically what this stress is, it's a normal stress that the beam experiences as a result of the internal bending moment. Okay. Okay. And so the equation for it is very simple. Okay. And so it's going to be m, which remember is a function of x, okay, times dy, d sub y, and I'll define that in a second, divided by I. Okay. This d sub y here is going to be our distance from the center line of the beam. Okay. Right, and so if we draw a beam cross section just like this, okay, we kind of draw the beam center line just like that. Okay. dy is simply going to be just any distance that's up, from here. Okay. And so basically what this equation is telling us is that, across the cross section of the beam, if we kind of go vertically or transversely up and down, then the bending stress is going to vary. Okay. And in fact, if we say that the bending stresses are something like this, or bending moments, sorry, if the bending moments are something like that, and those are needed to maintain equilibrium, okay, what that tells us is that, if you can imagine, you take kind of a rectangular block and you kind of take it and you kind of try to squeeze it up kind of like this, kind of like what the bending moments are doing. What you can imagine is that the top of this beam is going to be compressed because you're kind of bending it that way. And the bottom of the beam is going to be in tension, okay? Yeah. Actually, I think Charlie, I think you asked a question about this last week too, about what the stress distribution would look like in the beam. And so it would kind of look something like this. Right? And so if we kind of use the middle of the beam as kind of a 0 point, okay, the stress distribution might look something like this. Or the bending stress distribution. Okay. Then we can draw the same thing on this side here.
So the top and bottom would have the same value for the
Yes,
stress?
top and bottom have the same value, but opposite sign, because one would be in tension and the other one would be in compression. Yep. Okay. And so actually, this dy here is actually, you can think of it as like a coordinate, right? So above the midline here, you can say that dy is positive, okay? And then below the beam midline, then dy is going to be negative, okay? And so, the bending stress is going to change sign once you cross the midline. Yeah. Mhm. Right. All right. And so if you notice from this equation here that when we're at the midpoint of the beam, the bending stress is actually 0. Okay. It's because in the middle of the beam, both the tension and compression are basically going to cancel each other out perfectly. And so, actually in the middle of the beam, you have 0 stress. Okay. And so sometimes we give the midline of the beam a different name. Okay. And so a lot of times the midline of the beam is called the natural line. Okay. And what natural line means is that there's zero stress. Okay. And so there's there's a little bit of a nuance and distinction here. So when I say midline of the beam, I mean kind of the geometrical midpoint of the beam. Okay. And so geometrically, if you take the cross section beam, you find just the centroid of that. That's where the midline is going to cross. Okay. And then there's also natural line. And so natural line just means that there's 0 stress here. Okay. And so for a straight beam like this, the midline and the natural line, those two are coinciding. And so those are basically the exact same thing. But later on, we'll look at cases where we have curved beams, where the natural line is actually going to move away from the midline of the beam. Okay. But for straight beams like this, you can consider them to be exactly the same, because the geometric midpoint is also exactly where we have zero bending stress in the beam. Okay. Okay. Any questions on this? Okay. All right. And so that's kind of a classical beam theory. Okay. And so for classical beam theory, you have your shear, you have your bending moments, and you have your bending stresses. Okay. Now let's look at a couple more more specialized cases. Okay, where the solution will change slightly. All right. So first, let's consider thick beams. Okay. And so by thick beams, I mean beams that are have a larger cross section than usual. Okay. Specifically, they're larger than normal in the transverse direction. Okay. Okay. And so basically, you're going to have beams that are that vary away from the midline a lot more than normal. Okay. And so in these situations, you're going to have pretty significant bending stresses that that develop. Okay. Okay. And the reason for this is that we're going to have we can potentially have very high values of dy. Okay. Okay. And so in these cases where we have, a lot of bending stresses, the beam itself needs to develop some more internal stresses in order to maintain equilibrium. Okay. Okay. And in particular, the stress that comes out of thick beams like this is going to be a horizontal shear stress. Okay. Right, and so schematically or visually, let's kind of draw, what we have here. Okay. And so let's say that we have a beam cross section and we have our internal bending moments that look like that. Okay. And so if we take kind of a horizontal slice of the beam, not somewhere at the midline, because we know the midline has zero stress, but if we take a slice down there, okay. In addition to the bending stresses that are present, you're going to have a pretty significant horizontal shear. Okay. And so this tau that I drew here, you'll notice that's going in the horizontal direction, right? And so it's not transverse, it's axial. Okay. And so this is a horizontal shear stress. Okay. All right. And so you can work this into the beam equations. And so we're not going to do that, but I can give you the solution for this on the next page. Okay. And so this horizontal shear is going to vary as a function of dy. Okay. And so it's going to be different at different parts of the beam. Okay. That's something you need to account for when you have thick beams like this. Okay. Okay, so any questions on this so far, or why why this horizontal shear develops in these beams? Okay. All right, and so the equation for this is given by the following. Okay. So if we say tau of dy, okay, and so this is a function of the transverse distance. This is equal to v. Remember, v is the transverse shear, okay, divided by I times h squared divided by 8 minus dy squared divided by 2. Okay. Okay. And so you can see from this equation here that this transverse shear depends on v. Remember, v here is the transverse shear on the beam cross section. Okay. And also depends on I, where I, remember, is our moment of inertia. Okay. And this h, I don't know if we've defined this yet, but h here is the height of the beam. Okay. Another way you can think of H is kind of the maximum value for dy, okay? And so for any given cross-section, dy has a maximum of H that it can maintain, okay? All right. Okay. Any questions on this equation here? Okay. All right, so those are thick beams. And so for thick beams, you need to take this horizontal shear into account. Okay. Now let's talk about curved beams. Okay. Right, and so curved beams are beam structures that the cross section it's kind of bending like this. Okay. And so your beam might look like this. So very common in practice, right? So if you're making any kind of structure that requires any curvature, then you're going to have some curved beams, right? I know for sure that for those of you on Baja, I know that a lot of the structure of your vehicle has a lot of curved beams like this. Okay. And if you read the notes, these notes are written for a biomechanics class, and so if you consider your rib bone as a curved beam, then this theory would also apply here. Okay. All right. And so we're only going to talk about kind of the modifications that you would make in general. But because the beam is curved like this, like we said earlier, the midpoint of the beam and the natural line kind of deviate from each other. Okay. And so one way we can sum that up is that the bending stress at the midpoint of a curved beam is no longer zero. Okay. And so, what's happening is that the natural line or the line of zero stress is actually moving towards the inner curve of the beam. Okay. Right, and so if we want to draw this, first let's draw the midline. And so the midline is still kind of exactly the same as before. Okay, so it's going to be in the exact midpoint of the beam. Okay. But the natural line, or the line where there's zero bending stress, that's going to move slightly down. Okay. So this green right here, this is the natural line. Okay. All right, and so this actually breaks some of the assumptions that we had in our previous equations. Okay, and so our equations for things like the bending stress are gonna vary here. Okay. Okay, and so I'll give you those equations on the next page, but I kind of need to redraw this figure because it's there's kind of a lot of distances that we need to know. Okay, so before I do that, are there any questions on this? Okay. All right, so let me go ahead and redraw the figure for you, just so that we can we can have all these distances. Okay. It's a little bit of a neater picture here. Okay. Let me go ahead and draw the midline here in red. And then the natural line I'll draw in green. All right, so let's draw some distances on this thing. Okay. All right, so first let's consider distances with the natural line, right? So the natural line is moving down, and so now the amount of beam that's above the natural line and the amount of beam below the natural line, those are different. Okay, and the way that we can characterize that is with these two distances here. Okay, and so the distance from the outer curve of the beam to the natural line, we'll call that C0. Okay. And then the distance from the natural line to the inner curve of the beam, we'll call that C1. So C0 and so let me draw this down here a little bit. So C0 and C1 are distances between natural line and top and bottom of beam. Okay. Next, we have the distance between the midline and the natural line. Okay, and so I'm talking about this distance right here. Okay, and so this is kind of directly a measure of how much the natural line shifts down from the midline. Okay, and so we'll call this distance epsilon. Okay. So epsilon is distance between natural line and the midline. Okay. All right, and then lastly, what we need are the actual radii of curvature for the outer surface and the inner surface. Okay. And so if we draw kind of a centroid here, so we'll call this O. Okay. This radius of curvature of the outer part of the beam we'll call RO. And then this radius of curvature here we'll call RI. Okay. So RO and RI, these are the radii of curvature of the inner and outer surface of the beam. Okay. Okay. All right, and so with all those defined, we're ready to compute the bending stresses on the inner and outer curves of the beam. Okay, so any questions on the variable definitions here? Okay. All right. And so with those, we can compute the normal stresses, the normal bending stresses on the inner and outer curves. Okay, so let's start with the inner one. Okay, so sigma I is going to be M times C1 divided by epsilon A R1 or RI. Okay, for this A right here, this is the cross-sectional area of the beam. And then we have sigma O. This is the bending stress on the outer surface of the beam. This is going to be a minus M CO divided by epsilon A R O. Okay. And so you can see here that the main difference between these guys, these equations look very similar, But the only difference is that, one equation has C1 and Ri, the other equation has CO and RO, okay? And the sign is flipped. Right. And so basically, we modify these equations, or the modification that we're making is mostly due to, two things. So it's due to how much the natural line moves down, okay? And it's also due to, the actual radii of curvature of the beam itself, okay? And so those are the two kind of main factors that modify our bending stress calculations for curved beams. Okay, any questions on this? Okay. So I know there's a lot of equations today, and I'm kind of highlighting them to you guys just from a perspective of, you should know kind of which factors affect which inside these equations, right? And so, because this is a finite element class, we'll be doing mostly everything with finite elements. And so, you're not going to be actually using these equations to compute anything. But, what I want you guys to get from this is to have an understanding of which factors will affect which other factors, right? And so when I present an equation to you like this, I'm highlighting that, this factor is in the numerator, this one's in the denominator. There's a negative sign here, okay? And so those are the kinds of things that I think are really useful for, for engineers that work with computational methods, because, the computer's going to be doing all the hard calculations for you. And so you're not going to be doing any of those yourself. But, you should have an intuition, you should have a sense of, if I increase the bending moment, or if I increase the curvature of this beam, then that's going to affect my solution in this way, okay? Okay. All right, and so that's that's curved beams, okay? And so the next thing I want to go over is I have kind of a really big ass table for you here that shows a lot of some very common beam situations and what some key solutions are, okay? And so I don't know if I'm going to cover all of them in the class today, just because it's kind of a lot. And so on the notes I have, 7 different beam situations, and that's not even all of them. I got lazy, I just stopped. But this is I think some of the more important ones to know. Okay, and so again, with this big list right here, I want you guys to focus on, if I have a situation that looks like this, what kind of general behavior can I expect from this solution, right? So where is the max stress going to be? Where is the max displacement going to be? What is approximately what its value is, okay? And so let's go over some of these. And so, a table like this is really useful, not because it's going to cover every single situation out there. That's impossible. But again, you can, a lot of situations you can kind of approximate to something like this, and then that's going to give you kind of a good idea of what to expect from the solution. Okay. All right. And so the first common beam scenario I want to go over is a simple cantilever beam with a load that's concentrated at the end. Okay. Okay. And so visually it looks like this. You have a beam that's fixed to a wall. And so that's the definition of a cantilever beam. Okay. And then the other side is completely free. And then at the tail end, what you have is a concentrated load P. Okay. The length of the beam is given by L. Okay. And then just for clarity in how I'm expressing these solutions, I'm going to call the left side of the beam A. Okay. And so that'll be side A. Actually, let me give it in lowercase just so that we don't get confused with cross-sectional area A. Okay. And the right side of the beam will be B. Okay, lowercase b. All right, and so for these solutions here, I'm going to give you what the value of the maximum displacement is. Okay. Okay. And so there will be a formula for that. And then I'm also going to give you the maximum bending moment. Okay. All right. I'm going to give you their values and also their locations. Okay. Okay. And so let's talk about the max displacement first. So the max displacement is going to be P times L cubed divided by 3 EI. Okay. And E and I here have the same definitions as before. So E is our Young's modulus, and then I is our moment of inertia. Okay. And where this occurs, the max displacement, okay? Or I guess, we can kind of think about this actually too, right? And so this cantilever beam, even though the load is transverse here, so obviously it's pointing down, but in terms of how it's fixed, it's very similar to our first ANSYS activity, right? So on one end, you have a completely fixed support, and on the other end, that's where our load is being applied, okay? So even though the load is in kind of in a different direction here, we should kind of see similar kind of behavior because those two situations are a little bit analogous, okay? And so just like we saw in our ANSYS activity 1, this maximum displacement is going to happen at the end of the beam, right? Or where the load is being applied. And so this is going to be at B. Okay? And so the maximum displacement is going to occur at the right side of the beam, which is furthest away from the fixed support. Okay. All right. So that's the maximum displacement. So now let's go over the maximum bending moment. Okay. And so this one's pretty simple. Okay. And so since the beam is rigid, the maximum bending moment here is going to be the moment that's needed to maintain equilibrium. Okay. And so if we do kind of a free body diagram on this, we know that there's going to be a bending moment that that the beam has to develop with the fixed support. Okay. And so it's going to go something like that. Okay. Okay. And so that moment there has to cancel out the moment from the load. Okay. And then and so if we compute that moment based on the load, it's going to just be the product of P times the length of the beam. Okay. And then from this free body diagram, we know that this maximum bending moment is going to occur at the left side of the beam A. Okay. All right. Question. So the question from the chat is: Will these beam equations appear on the exam? And so I'm not going to ask you to write out the equations or to use them to compute anything. Again, these are used for kind of for intuition. Okay. And so one way this might appear on the exam is that I might just give you this figure right here. Okay. Right. I might just give you this figure, and I might ask you to tell me where do you think the maximum displacement is going to occur, and where do you think the maximum bending moment is going to occur. Okay. And so that's the kind of qualitative intuitive conceptual knowledge that I want you guys to take away from this stuff. The formulas themselves are not for me and for this class are not that important, but what's more important is is getting this intuition of how these kinds of slender structures are going to respond to external loads. Yeah. All right, question. So the P, is that P for pressure or for load? So in this case, this P here is for a load. And so P here has units of force. Yeah. It's a concentrated load. Mm-hmm. Okay. And so that's the cantilever beam with a concentrated end load. So are there any other questions on this before we move on? Okay. All right, so that's the first one. Right. So now let's go to the next one, which is a cantilever beam with a uniform load. Okay. And so geometrically it looks similar to our last case, but this time the load is going to be distributed across the entire beam. Okay. We'll draw them on red to be consistent from before. Okay. Right. And so now our load is not concentrated at the end, but now it's distributed throughout the entire beam. Okay. And we'll give this the symbol Q naught. Okay. This beam is going to have a length L. Okay. The left side of the beam will be A and the right side of the beam will be B. Okay. And so just like before on the previous page, we can compute the maximum displacement. Okay. And so the maximum displacement of this beam is going to be Q naught L to the fourth divided by 8 EI. Okay. And then the maximum bending moment, this is going to be minus Q naught L squared divided by 2. Okay. Right. And so now let's go. Now let's quickly mention about where these are going to take place. Okay. And so the maximum displacement. And so since the supports here are exactly the same, right? And so we only have one fixed support on the left side. Then this tells us that the maximum displacement is probably going to be at the location which is furthest away from the support. Okay. Okay, so the max displacement here is going to occur at the right side of the beam. Okay, so that's going to be at B. Okay, and the maximum bending moment again is going to be at A because that's where it's supported, and that's where the biggest reaction force is going to take place. Okay. All right, and so those are the two kind of main cantilever solutions. Okay, so I'm going to skip ahead a little bit just to just to give you guys a little bit of a different look. Okay, and so now let's consider a simply supported beam. Okay, and let's consider a simply supported beam with a concentrated center load. Okay, and so a simply supported beam is a beam which is fixed on both sides. Okay, but instead of a fully fixed support like this, we have a pin and a roller. Okay, and so visually it looks like this. Okay, actually on the left side, that's where we have our pin, and the right side we have a roller support. Okay. So this is a pin support. This is a roller. And so the biggest difference, between the pin and the roller versus the fixed support that we see above, is that pin supports and roller supports don't constrain any kind of they don't supply any kind of reaction moments. Okay. And so that's going to affect our internal bending moments on the inside. Okay. Okay. Okay, and so let's go ahead and draw our concentrated load. Okay. And so since both ends of the beam are supported now, so both of those are going to have a zero transverse displacement. Okay. And so in order to actually get something interesting, we have to apply the load at the middle of the beam. Okay. All right. So just like before, we have the length of the beam given by L. Okay. And the left side of the beam we'll call A, and the right side of the beam we'll call B. All right, so the equation for the maximum displacement is going to be, our maximum displacement is going to be P L to the fourth, okay, divided by 48 EI, okay. Right, and so that's how you compute how much the beam is going to displace, okay. Location-wise, this is going to occur at the part of the beam where the load is happening, and also the part of the beam which is furthest away from the support. Okay. And so since we're supported here on both sides, the part of the beam that's furthest away from them is going to be at the middle. Okay. And so our maximum displacement here is going to be, at the center of the beam, which is where the load is applied, and which is furthest away from the supports. Okay. Yep.
That's LQ.
Yeah, L to the fourth, sorry. Mhm. Okay. And so now let's do M max here, okay? And so this is going to be P times L divided by 4. Right? And once again, since both the supports there can't supply any kind of reaction moments, okay? Then the moments at those locations are actually going to be 0, okay? Because there's 0 reactions there. And so the maximum bending moment here is actually going to occur also at the center of the beam. Okay. Right. And so if I draw kind of an exaggerated look at what the beam looks like after it's been displaced, it's going to look something like this. Okay? And so it's going to be kind of this, kind of this bowl thing, okay? And so what's happening here is that, because the middle of the beam is being depressed a lot, in order to maintain kind of equilibrium there, the beam itself has to exert kind of an internal bending moment to kind of cancel out that kind of high curvature in that location, okay? And so that's why in the case of a simply supported beam, both the maximum displacement and the bending and the maximum moment are going to occur at the same location. Okay. Okay. Any questions on this? Okay. All right. So I have 4 more different beam solutions in the notes, but I think with just these 3 examples here, I think the point kind of gets across, right? And so again, the exact formulas and the exact numerical values for these, I'm not that concerned about, and I'm not going to quiz you on that. But I want you guys to just to kind of get this intuition of the relationship of where my supports are, where are my loads, where is my max displacement, where's my max stress going to be, okay? Because that knowledge is going to serve you really well. Because when you're doing finite elements, next week we're going to start getting more into the actual how do we fiddle around with the settings and what do certain settings do, right? What you'll discover over the next few weeks is that there's a lot of ways that your finite elements can get messed up, okay? And so it's really important to have a good conceptual understanding of kind of the physics behind these situations, so that you can look at a finite element solution and be like, that doesn't look right. And if something doesn't look right, then you can go back and see, maybe I need to fix my mesh, my boundary conditions, okay? Because that's really important, because with finite, because ANSYS is not going to tell you. So ANSYS is just going to compute the solution as you say it, but it's not going to tell you whether it's right or wrong. Okay, so you guys need to kind of determine that as the engineer. And so having these kinds of having this kind of background, even though I know it's not the most exciting thing to go through, probably some stuff you've seen before, but it is really important. And it's, I think, an underrated aspect of being a finite element engineer is to actually interpret your results and determine whether they're good or not. Okay.
Excuse me, Professor.
Yep.
Are we going to just model all our ANSYS activities with these simple models, right? All the structural, they all going to be a model with the beams, right?
So our next activity will be very similar to a beam, and that's kind of the reason I'm going through this, is so that when we go through the beam exercise, you'll be able to look at these situations. And so some of you might have seen the activity already, but basically the way your beam is going to be loaded is going to be very similar to this situation 1 right here. And so I'm going to have you guys fix the beam on one side and then apply a load on the other side. Okay. And what you'll see is that the maximum displacement is going to be exactly at the right side of the beam where you have the load being applied. But future activities, they're not going to be as simple as this. But for a lot of engineering structures, there are going to be parts of the structure that look like a beam. And so as an example for activity 3, what I have planned is to have you guys model a kind of a freeway signpost. Or I guess we can make it more exciting. We can make it one of those giant jumbotron things that Cal State Fullerton has on the side of the freeway. And so even though those signs, it's not a beam exactly, but the post part of the sign that can be modeled as a beam. And so for that part of the structure itself, you can use a lot of this theory to kind of check your results and to make sure that they're okay. Yeah. All right, and so the last thing I wanted to cover today is kind of a little bit more of a niche situation. And so, it's not, this is not that, I would say this is a lot more common in automotive engineering than anything. But we're going to talk about torsion and torque, okay? Because when you take a bar, you take a rod and you put it under torsion, that's also going to develop some stresses on the interior of the structure. Okay. Right. And so visually, it looks something like this. Okay. So let's say that you have a cylindrical structure. Okay. And when I say torsion, what I mean is that if we consider this dotted line here to be kind of the long axis of the rod. Okay. A torsion is going to apply a load that's kind of like a twisting load, okay? And so it's not a bending mode, and so we're not going to be bending this. We're literally going to be taking it and kind of like twisting it with our hands, okay? Actually, let me use red just to be consistent. Okay, and so we're going to apply a bending torque or a torsional torque T, okay? And on the other side, we have an opposite. And so this is a different kind of loading than what we've been looking at for beams, okay? But it's still going to produce some stress, okay? And in particular, this torsional loading right here will produce predominantly a shear stress. Okay. And the formula for the shear stress is going to be tau, which is equal to T, which is the amount of torsional loading that you're going to apply, times R divided by J. Okay. So we have a couple new variables here. So R here, this is just simply the radius. Okay. And so for the simplest torsional case, you know the radius of your rod. Okay. And this J right here, this J kind of serves a similar purpose as I for our beams. Okay. And so this J right here is called the polar moment of inertia of the bar. And so the way you compute J is different than how you compute I, but it serves kind of the same role. Okay. And so based on the shape of your cross section, and so whether you have a circular one or an oval one or a ellipsoid one or a star-shaped one or or whatever, and so that shape is going to impact how stresses develop inside your structure. Because the shape, just like moment of inertia, and so the shape basically changes how mass or how matter is distributed throughout your cross section. Okay, and that's really important because the way that the mass is distributed has a big impact on how the internal structure kind of develops internal stresses. Okay, right, and so that's for a thick bar, and so we can also find the same equation for a thin wall bar. Okay, so let's say you have a thin cylindrical shell. Okay. So let's say that you have a hollow tube like this, okay? And so just like before, we're going to apply a torsional loading on this. But now another quantity that we're going to need is the thickness of this of the shell. Okay, so this T right here is a thickness. Okay. And so if we take these and then plug it into or we solve the equations of elasticity, our solution for the torsional shear stress is big T divided by 2 little t A. Okay. Where the only new addition here is A, and this A is the cross-sectional area. Okay. Right, and so these are your solutions here for the shear stresses that occur when you have something under torsion. Okay, and so again, the place where I kind of see this most often is in automotive, and so in those cases you have a lot of shafts that go into your engine, and those are exposed to a lot of torques, right? And so those torques and torsional loadings will produce shear stresses that look like this. Okay, and so if you're doing finite elements with kind of some automotive flavor to it, or automotive application. These equations will be useful for you to check your work. Okay. All right. Any final questions on anything we covered for today? Okay. All right. So that's all I had planned for today. And so thank you guys for coming, and thank you guys for tuning in. And so when we come back on Thursday, we're going to be doing our next ANSYS activity, right? And so again, I'll send an email to remind you guys, but there's kind of a lot to cover on Thursday, and so. If you guys can have Workbench open at the beginning of class on Thursday, that would be great. Okay. And so have a great evening, everyone. And I'll see everyone on Thursday for our next ANSYS activity. Yeah.
Can I stay in class tonight, like after the classes?
Yeah. So I'm technically supposed to mock up after the class, but I've been telling people I'm okay with people staying here. The only thing is, if you're the last person, just make sure to close the door and lock the door and turn off the lights. And of course, don't trash the place, but
Sure, yeah.
Chris.
Thank you, Professor. We'll see you Thursday.
What's up?
I was just saying, thanks. We'll see you on Thursday.
All right. Yep. See you Thursday, Stephen. Thanks, guys.
I can't find the full body circuitry system of
Okay.
the one.
Okay. Yeah. For sure. I actually do need to. Okay, I'm the last one.